So we have our target here. We're looking at this analysis of variance and called ANOVA, as I said. The purpose of this is to compare several means against each other. And you're going to see some similarities today between ANOVA and what we did with chi-square. In chi-square, we were looking at several ways that categorical variables could be broken down, and we were testing in the big picture to see if there was a relationship. And very quickly, using the technology, we got our chi-square statistic, we got our p-value, but really the analysis just began there. If it came back as a significant relationship, then you had to start to dive in and look at the differences, look at those chi-square contributions in order to determine exactly where is that relationship occurring. That was with categorical data looking at proportions. Here, with ANOVA, we're looking at multiple things happening, but it's quantitative data and it's means. We're testing to see if there are significant differences between the means in different sets of data. Okay? So that we have that comparison at least to kind of match with what's going on. Now, again, kind of like what we saw with chi-square, we looked at why do we not just use our two sample procedures for comparing two things against each other, and picking and choosing and making those comparisons. Okay? Well, we had two sample t procedures to compare two populations or the mean responses of two treatments in an experiment. Okay? But we're, again, taking a step back to look at the big picture, because if you're just looking at these two, well, what about this third one? How is that impacting the overall dispersion? Okay? Or a fourth one, or a fifth one. The example problem that we're going to use as our framework in this lesson is on the Caribbean island of Dominica. The tropical flower there that they have, called a heliconia, it has a few different varieties that over time, these varieties have some distinguishing characteristics in terms of like the length of those flowers. And because this island, I mean, we're talking like little Darwinism here, because this island is fairly isolated, the hummingbirds on that island, that over the span of centuries or millennia, my evolutionary biology is a little rusty here, but over time, these different species of hummingbirds have evolved so that they can fertilize specific types of these flowers. So essentially, researchers wondered if the lengths of the flowers and the forms of the hummingbirds' beaks have evolved over time to match each other. Now, what we have is a table of data that gives the lengths of the measurements in millimeters for samples of 3 varieties of heliconia. Each is fertilized by a different species of hummingbird. We want to know if the 3 varieties display distinct distributions of length. In particular, we're looking at the mean. Are the mean lengths of their flowers different? Now, we have our raw data right here. Our 3 varieties of the heliconia flower. We have this thigh-high variety, we have this Caribia red, and we have this Caribia yellow. So the raw data is what it is. To kind of plan out where we're going with this and what this analysis is going to look like, we'll start by looking at some statistics. We'll start by looking at some displays of this raw data to see kind of what's going on and where we should go with this analysis. Now, we can start looking just at like the 3 sample sizes, the 3 means, and the 3 standard deviations to get an idea of what's happening with this comparison. So we have our 3 varieties, Baihai, red, and yellow. They're all different sample sizes, but that's okay. We know at this point you do not have to have identical sample sizes in order to compare. Looking at the means, okay, this first variety, this Baihai, 47.6 millimeters, that's by far the longest of the averages. The other 2 varieties, the red and the yellow, they're both in the 30s, and they're much closer together, 39 and 36 approximately. But we know that mean alone is not enough for comparison. We also need to look at the distribution, the variation within those data sets. And that's where standard deviation comes into play. You'll see that this red variety, it had the middle mean length, but it has the most variability within its flower. Okay, standard deviation of 1.799. Compare that to the yellow variety, there's much less. There's about half the variation with that yellow variety, 0.975. The Baihai variety, which we said had the longest average, it's in the middle of the pack in terms of the standard deviation. So there's a lot of things going on here. We want to get beyond just the numbers and start to look at some visualizations to help facilitate this comparison. So here we have a stem plot of our 3 distributions. And again, we're starting small at the top, longer lengths on the bottom. We see the Baihai at the top end, the red varieties in the middle, the yellow varieties on the short end, and the red and the yellow are closer together. We don't see a lot of the standard deviation displayed on this type of a distribution here. And it also is worth mentioning that we have different sample sizes. This red variety was our largest sample, and it also happens to have the largest standard deviation. So is that just a coincidence, or does that kind of facilitate one over the other? In terms of how this is a little bit more spread out, you can see a little bit with the range here. We can kind of do a quick calculation in our head. And this middle red variety goes across 7 different numbers. This just went across 5 different values, none in the 49s. The yellow variety was across 5 different values as well. But again, we have no idea right now if these differences are statistically significant. We see differences, but who's to say if that difference is significant? We have the histograms along the left side here. We also have the box plot. We're going to be looking at some box plots today because it helps facilitate our comparison of 3 different things. Now remember that we were just talking about mean and standard deviation. The box plot is a representation of the median and the 5-number summary, the quartiles. So it's a more, probably using this word wrong, it's more like palpable way of measuring variation. As opposed to standard deviation, it's just a number. We're used to seeing that with the normal distribution. But here, we know that we have a quarter of the data in each of these segments here. So in that red variety, where we have a lot of variation, look at how that quarter is spread out. But opposed to this yellow variety, where we do not have much variation, all of this is very condensed around the center of that distribution. So it's worth keeping in mind how not only do the means differ, but also the variation within each set. Because you'll find that with ANOVA, both of those are key in terms of understanding this comparison. We'll revisit some box plots in a little bit here. So we have our 3 sample means. The null hypothesis, we know, is always a form of equality, saying that things are the same. So we have been saying that 2 things are the same. In the case of ANOVA here, we're comparing these 3 means. We're going to say that the true means for the length are all the same for all the groups. So mu1 equals mu2 equals mu3. Now, we had said our other way of starting to analyze this was to just do separate t-tests and only pick 2 at a time. So compare mu1 to mu2, and mu1 to mu3, and mu2 to mu3. But the problem, if we were to take that approach here, is, okay, what if mu1 and mu2 are the same, but mu1 and mu3 are different, and mu2 and mu3 are the same? Like, how do they play off of each other? You're looking at how all of these are related to one another. So to just isolate 2 for the sake of comparison, you're missing out on the larger scale, the big picture here. And this gives rise to the problem of multiple comparisons. We saw this problem with chi-square. The only difference with chi-square, we were looking at categorical data and proportions. Here we're looking at quantitative data and means. Now, this exact same slide appeared in our lesson on chi-square, talking about multiple comparisons. And the statistical methods for dealing with multiple comparisons usually have 2 steps. An overall test to see if there's good evidence of any differences among the parameters that we want to compare. And then, once you get that initial test performed, we have a detailed follow-up analysis to decide which of the parameters differ and to estimate how large those differences are. Same kind of thing here. Back in chi-square, we got our chi-square statistic, we got our accompanying p-value. There either is no relationship, but if there is a significant relationship, that's when we started to dive in a little bit deeper, look at the individual differences, look at the chi-square contributions, the ones that were highest in contributing to that overall chi-square statistic, and that's where you might identify 2 things that you wanted to do a difference of 2 proportions z-test for. Similar kind of thing right here. We're going to perform our overall ANOVA, and then from there, maybe we can isolate certain relationships that we want to actually follow up with and do a more detailed analysis. Okay, some of that will be in our next lesson on Monday. For ANOVA, we have a new distribution. It's an F distribution, and I'll show you a picture of that in a second when I pull up GeoGebra. The F distribution is heavily skewed to the right. So it's not symmetric, it's not something that is like necessarily inherent to you, but we'll take a peek at what that looks like momentarily. As we said, our null hypothesis, we want to test that there are no differences, so that the first mean, mu1 equals mu2 equals mu3. And you could keep this going to compare 4 means, 5 means, whatever. Okay, but they are all equal to one another. They are all the same. Now, the basic conditions for inference are that we have random samples from the 3 populations. Okay, that's pretty much going unstated, that we know that we have randomly collected data in all of our samples, and that in this case, the flower lengths, they are normally distributed within each population. Okay, so we're kind of making an assumption in those cases, but the flower lengths, we said natural measurements tend to be normally distributed. Okay, so we have that going here. Now, the alternative hypothesis in this test of ANOVA is that there is some difference between these means. Okay? It's very tempting to want to say, all right, this equals this equals this. Well, the alternative hypothesis is that mu1 is not equal to mu2 is not equal to mu3. And that's not completely true. The reason is that as part of this alternative hypothesis, we could have mu1 equal to mu2, but not equal to mu3. Or mu2 and mu3 are equal, but not equal to mu1. It's okay to have some that are the same. But if one is not the same as all of the others, then that's the alternative hypothesis here. Okay? So think about that for a second. That is the same as that is the same as that. You're not saying that they're all different. You're saying that at least one is not the same as the others. Okay? That there is some difference between these means that we are comparing. Okay? That's important to recognize. Okay? We're used to establishing the alternative hypothesis is either one-sided or two-sided. We can kind of think of this one as being many-sided because we're not completely sure where that difference is occurring. Okay? And that kind of falls in line with the generality of this test of ANOVA. Okay? Is that it gives you a quick answer. Okay? There's no difference between these means, or there is some difference. Once you know there's some difference, now you have to dive in a little bit deeper and examine that difference. So, in our flower example, we're going to take a look at the technology here and then come back to this slide to show our conclusions. What you're going to see here, I will say, some of the numbers, we don't know what it's describing just yet. Okay? We're going to kind of get an idea of what this looks like and then kind of fill in the blanks moving forward into our next lesson. So let me start with GeoGebra here. Okay, so in GeoGebra, we're going from the spreadsheet perspective, and all our entry is our three sets of data, our three types of flowers here, the bi-high, the red, and the yellow, and we have all of those values listed out there. Now, we're going to select this data and come up here to our multiple variable analysis. This is a drop-down menu. Okay, one variable, the regression we could have started to look at there. There's a probability calculator. We want this multiple variable analysis, confirm our three columns, and we get this. So we have stacked box plots, which we saw a little bit of this in our first semester when we were first starting to play around with GeoGebra. And we can see a little bit about the variation in our data. And that first one, that bi-high variety up here, we see that kind of stands apart from the rest. We had also mentioned that this middle variety, the red one, it has the highest standard deviation. We see that. We've got 25% of the data in this broad margin right there, as opposed to these others, like 25 in there, 25 in there, 25 up there. We see some differences. Down below in this menu, if you don't have that, you're clicking this little sigma X up here to show the statistics. This is just the descriptive statistics, mean and standard deviation, as well as the 5-number summary. for each of those sets. We are going to change this. From that drop-down menu, we have ANOVA. Okay, so you make that selection, and it gives you this table right here. Now, there's a lot of data that's going on in this, and we'll need to talk about this more completely on Monday. But we have degrees of freedom over here. We have sum of squares. We have mean of squares. Here is that F test statistic, 259.1193. That is our F statistic. Its accompanying p-value. Okay. We have our hump. I'll show you this distribution in a second. We have our hump, and then the tail that extends far out to the right. 259 is way far out to the right. The data at that point on the tail and further out to the right is essentially zero. It's an extremely small amount, which is telling us in this case that we have differences in our means, okay? Meaning that they are not all the same. Okay? Maybe these two are close enough, okay? And that this one is the only one that's statistically different. We don't know at this point. Okay? But for right now, we have strong enough evidence to say that these three means are not all identical. The F distribution I wanted to show you. This is kind of what that F distribution looks like. Okay, we get a high peak on the low end, and then bringing this out to the right. Okay, you can see this only goes to 12 or whatever. Okay, much further out to the right, we were at 259 for our problem. Graphing calculator will also do this. On the graphing calculator, we're going to go Stat, Edit, and enter our data into our three lists in this case. If we had 4 things we're comparing, we would use 4 lists, 5 lists, however many we need. I think the calculator only has 6 built into it though. So, obviously you want to be careful with the data entry here. That's probably where a mistake would occur. You got all those decimal places to watch out for in this problem, which might be a reason to go away from the calculator and go with something that's spreadsheet based. Excel would do this as well if you had that add-on pack like I talked about. But to perform this analysis, second, quit out of this, we're going to Stat and over to Tests, and the very last option is ANOVA. You'll also see that letter E is a 2-sample F test. That uses this F distribution. However, it is just comparing 2 samples to one another. In this case, we need to compare 3. Okay, so if you're comparing more than 2 items, you're using this bottom option of ANOVA. And you'll also notice that when we select ANOVA, we don't have our usual input screen. Instead, it's just old school open parentheses. We need to tell it which lists we are comparing. So we're going to go second L1, comma, second L2, comma, second L3. We can hit enter. And here's our important information. There's that F statistic, 259, and the accompanying p-value, 1.91 times 10 to the negative 27th, which means that it's 0. Okay, it's essentially 0. This precision is impractical in a real-world sense. If we had perfectly normally distributed data, then yes, that would be the p-value times 10 to the negative 27. Okay? We never have anything that is perfectly normal. So what we can get from that is that p-value is extremely low. It's going to be significant on any alpha level, 0.05, 0.01, 0.001, etc. Okay? It's essentially zero. That's what's important to us. Now, these other statistics here, we'll get into some of this on Monday. This is what we will see, what we saw on that chart in GeoGebra, and this is what Pitt wants us to look at a little bit if you're taking that test. Start to analyze these degrees of freedom, sum of the squares, mean of the squares, for both of these factors here. Okay, the other one, you'll notice we have two different degrees of freedom. We had 2 up there, 51 here, sum of the squares, mean of the squares, and then a standard deviation measure. Okay, we'll talk more completely about what that represents next time. Any questions up to this point with the technology or what you're looking for with a chi-square statistic, or not chi-square, F statistic or p-value? Okay. All right, so this is just confirming some of those results. Again, our F statistic, 259.12, a p-value that's incredibly small. Okay, it's significant on any level. We have strong evidence, very strong evidence, that the 3 varieties of flower do not all have the same mean length. Okay? And from just our preliminary analysis, it appears that the bihive flowers are distinctly longer than either the red or the yellow. Okay, we saw those red and the yellow, they were closer together. The red flowers were a little bit longer than those. This is the type of output that their statistical software Minitab would look like. So if you were provided with this snapshot on CHS exam, you can see we got our F statistic right there, p-value essentially 0. This is that table that we had seen from GeoGebra. We'll talk more about this. Degrees of freedom, sum of the squares, mean of the squares, and so forth. Minitab, which is the software they use, they give this comparison of confidence intervals. That is not something you need to worry about for ANOVA. They give you a visualization of if those confidence intervals overlap, to kind of give you an idea about the significance here. I just show you what the GeoGebra input and output looks like if you needed to refer back to this. And from our spreadsheet, we're selecting multiple variable analysis and box plots and pull down so that you see the ANOVA here. Graphing calculator, again, lists ANOVA from the stat and tests. Identify which lists you're comparing, and then we have our F statistic and our p-value right there. Now, again, to wrap up here, I want to explain a little bit about what ANOVA means, what's going on with ANOVA, and this we're going to talk more completely about next time. We have our test statistic. Okay, we saw what we're doing to obtain it. It can get a little bit confusing. This is what we call a one-way ANOVA. And there are different, more complex tests of ANOVA that can be done. And it says the details of ANOVA are a bit daunting. We'll get into some of that next time. But the main idea of ANOVA is more accessible and much more important. When we ask if a set of sample means gives evidence for differences among the population means, what matters is not how far apart the sample means are, but how far apart they are relative to the variability of individual observations. That's probably in one ear and out the other ear. it goes back to an idea that we said at the very beginning of the year, is that a lot of times people just want to put emphasis on the average value. Okay? This average is bigger than this average. But if you have a substantial size to that sample, just as important as the mean is the variation, in this case the standard deviation. How much variability do you have across those data sets? And that's what ANOVA compares. Okay? And to illustrate that again, I have two sets of box plots. Now, we have A and B, and these are symmetric sets of data. So remember, we're talking about mean and standard deviation, but a box plot displays the median and the 5-number summary. But when you have a symmetric set of data, like a perfect bell curve, the mean and the median are the same. So for us to talk about that in the same context here, these box plots all represent symmetric distributions. Now, the means, or the medians, these middle bars on the 3 box plots in A, they are identical to the locations of the middle bars, the means or medians, in B. You see the difference is the spread of the data. Okay, the variation among the sample means are identical, but the variation among the individuals within the 3 samples is much smaller in B. And we've got 25% in here, in here, in here, in here. Same thing going on in B, but the difference is in B, everything is right around that mean value. So our conclusion based off of this would be, if we were to perform a test of ANOVA on A and on B, because the samples in B contain a larger amount of variation among the sample means relative to the amount of variation within the samples, ANOVA will find more significant differences among the means in B. Okay? Think about what that's saying here. Okay. For in B, let's say we take, these are our 3 flowers again, we'll say. First, the high-bi, the red, and the yellow. If we were to take a sample of these high-bi flowers and know that they are all very compact around that average, it's extremely unlikely that we would get a sample mean that fits in like right here, that's in line with the sample mean of the other variety. Again, the null hypothesis in the background is that these 3 sample means are all the same. But for us to get something like that when there's more variation, okay, over here, if I were to get a sample mean from that high-bi variety, and there's a lot more spread in the data, this is not going to come back as significant. Okay? Maybe these means are all the same, because we cast a big net when we're looking at the variation in the high-bi variety, and in the red variety, and in the yellow variety, at least in this type of a distribution. Okay? But if everything is really condensed around the center, if you do get something that is distinct and different from what you would expect, because usually you get values right near the mean, right near the mean, right near the mean. If you were to get something that comes back there as significant, now you're saying that no, you have significant differences between these, that would be incredibly unlikely to have happened. Any of what I'm saying makes sense here? It's not just the means that you're comparing with ANOVA. Okay? And that's kind of the name of the game, right? My target, it says, perform an analysis of variance to compare several means. But if it was just as easy as looking at the means, okay, big, medium, small, done. There's our comparison. But it's called analysis of variance for a reason. You need not just the means, the differences in the means, but the differences in the distributions, in the variability of the data to come to these conclusions. Last thing here, of course the sample size influences it. Okay. We're pretending that the sample sizes are all identical in this theoretical example there, but larger samples will find more significant differences. What questions do you have up to this point? Next time, we're going to pick up right here and start to look a little bit more at what the details of that F distribution are like and what some of those values mean with respect to the problem itself and our interpretations of that test statistic.